All right, so let's start with this problem. Pretty simple problem. So I have a beam, simple supported beam, pin and a roller, two loads, 2-point loads, P and P, and they're spaced out at third points along the beam. I want to draw the shear force and bending moment diagram. Let's just think for a second. If I wanted to write shear force and bending moment equations, how many sets would I have to write? Could I write one set good for the whole beam?
No, 3.
Now I'd have to write a set that's good from 0 to L, a second set from L to 2L, and a third set from 2L to 3L. That could take some time. So what I'm going to show you today, I think, will be a little bit faster. The first thing I want to do is find my reactions. Now I'm going to draw a shear force and bending moment diagram. So what I'm going to do is come here and assume positive shear at A and positive shear at B. I'll let that soak in for a second. Remember, positive shear force, if I look at this left edge of my beam, it's going to try to make it rotate clockwise, and then look at B. It's going to do the same thing. It's down, but it's going to want to make it rotate clockwise. So both of those are positive shear forces. Now I'm going to come over here and write my equations of equilibrium and find out what those values need to be. So I'm going to start by summing moments at, I guess I should have labeled that A and B. I'm going to sum moments at A and make sure I'm in equilibrium. Okay, so looking at my applied loads, these two P loads, about A, what kind of moment do they create with right-hand rule? Positive or negative?
Negative.
Negative. So I have a negative P force. The first one has moment arm of L. The second one has moment arm of 2L. And then what kind of moment does this positive shear force at B create about A?
Negative.
Also negative. And it will have a moment arm of 3L. So when I solve for the shear at B, what do I get? I get P. Nope, negative P. So what does that mean? It means the shear force is negative at B, has a value of P. So we'll just hold on to that for right now. Then I'll sum forces in the y direction, and I should get my shear force at A. So looking at my values, I've got a shear force at A acting up. Up is positive. I've got a shear force at B acting down, shear at B. And I got two forces P acting down, minus P, minus P. And I want to put my result in there. So my minus and this minus cancel to be positive, and it looks like the shear at A is equal to P, positive P. So I have a positive shear of P at A and a negative shear of P at B. Okay, so what I like to do when I draw my shear force and bending moment diagrams is I like to create like a little template. So I'm going to draw a left edge. That's going to be my starting edge, x equals 0. I'm going to draw a right edge. That's going to be at x equals 3L. And then any other kind of interesting changes in my load I want to note. Now we already know that as I go from the left side of an applied force to the right side, what's going to happen? My shear's going to change, right? So that probably is a pretty important point. So I'm going to include that in my template. There's one here and one here. Another thing I would include is if I had other kinds of reaction forces, if I had the beginning or stopping of a distributed load. We know things are going to happen there. Just marking lines to help me draw a nice diagram. So my first action would be to establish my positive x direction on my graph and my positive shear direction. And I'm going to assume that all my shear values have some unit. I don't have units for these, but I'll just assume they're in kips. So I won't have to worry about carrying my unit around every number on my diagram. I'll just put all the units off here to the left. Now, do I know the shear force anywhere?
At A and B.
Yeah, so I know at the beginning it should be positive P. So I'm going to come over here and I'm going to put P. And what is it at B? It's negative P. So I know where I'm going to start and I know where I'm going to end. Just about every problem, you'll know that. You'll know where you're going to start. You'll have some starting value of shear or moment, and you'll know that has some ending value. So now it's up to you to use our differential and integral relationships to make sure that if I can start here, I can draw a curve that ends there. So the first thing we want to do is always say is the change in shear between any 2 points is the area under the load diagram. So looking at this first range L, and I go up and I look at the area under the load diagram. What is the area under the load diagram from 0 to just left of the P? Well, there is no load. So it's 0. So if I take P and I add nothing to it, what do I get? P. So the change in shear from 0 to L is 0, so there's no change. Now the derivative relationship says that the slope of my shear diagram is equal to the load. What's the value of the load here? 0. What kind of curve has a 0 slope? Horizontal line. So there's my plot for the shear diagram from 0 to L. You'll notice I'm not making any calculations. I am in my head because they're usually quite simple. Now, what happens as I go from the left side to the right side and I pass under this load P?
You go down.
Yeah, the change, in that case, the change in shear is equal to the load. And that load is positive or negative? Negative. So that means I'm going to go from P, I'm going to subtract P, and I'm going to land right here at 0. So just let you know, that change in shear is equal to minus P. So now I'm here. Now I want to calculate the change in shear from L to 2L. Well, the change in shear is the area in the load curve. So I go up to 2L. From L to 2L, what's the area in my load curve? 0. So if I start at 0 and add 0, I end up at 0. What's the slope of the curve that connects those dots? Yeah, because the derivative of the shear diagram is given by the load, and we know the load is 0, so I get a straight line. So there's really no shear in that middle section. Now going from the left side to the right side, what happens? It goes down P. So 0 minus P is minus P. The change in shear from here to here, well, I better land back at minus P. Let's see if I do. The change in shear between these 2 points is the area under the load curve. What's the area under the load curve between those 2 points? 0. We have found our way home. We left enough breadcrumbs. And what's the shape of the curve here? Is it just any kind of squiggle I want to draw? No. The slope of that line is equal to the load. The load is 0. 0 is a horizontal curve. And there is your shear diagram. Cool, huh? Yeah. Let's do it again. Except now that I have the shear, let's do the moment. So I'll establish a positive x-axis, a positive moment. I'll say all my moments will be in kip feet. And let's talk about moment. What is the moment at an external pin that doesn't have a point moment applied? It is 0. What is the moment at this external roller with no point moment? 0. So again, I know where I am. I know where I want to go. I need to connect the dots. So how do I connect the dots? Well, now we know that the change in moment between any 2 points is the area under the shear diagram. Let's see, there's an easy area to calculate. From 0 to area, what's the area of the shear diagram? What's a rectangle? Area of a rectangle is base times height. PL. So if I start at 0 and I add positive PL, I get PL. The slope of the moment diagram, which we know is given by the value of the shear. What is the value of the shear everywhere between 0 and L? It's constant. Constant value for slope is a straight line like this. In fact, if you actually looked at it, you would see that the slope is P. Why is it P? Because the shear diagram tells you the value of the slope. It's P. And it's constant. So now we'll go from L to 2L. The change in moment from here to here is the area of the shear diagram. What is the area of the shear diagram from L to 2L? 0. So PL plus 0 is PL. And what's the shape of the curve in here? Wiggle, 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 squiggle, squiggle, squiggle. No! It's given by this. It says that the slope is equal to the value of the shear. What's the value of the shear? 0. Zero slope is horizontal line. See, it's the same thing, just over and over and over and over. What's the change in moment from 2L to L? Well, according to our relationship, it's the area under the shear diagram. What's the area of this part of the shear diagram? Base L times height minus P. Minus PL. PL minus PL.
0.
Yay! Google Maps works. We found our way. What's the slope of the moment diagram? The shear, and the shear is minus P, so here's an equation that has a constant negative slope. And there's your moment diagram. That's pretty cool. By the way, if you look at this carefully, does this look familiar at all? Have we done something and loaded something this way in the past? Think back to the spring of when you took 11-12. Did you make a concrete beam by any chance? Did you notice this is the way we loaded it?
Yes.
Do you remember that the in-thirds had shear and that the maximum moment occurred in the middle? This is why. Back then I just told you this is why, but now you know this is why. It's called third point loading. It's a common test strategy because it does focus the maximum shear at the ends. That's where you had your diagonal cracking, if you remember. And then you had all your tension and crushing in the middle section because that's where the moment's maximum. Super duper. Questions?